Thank you for the introduction, and thank you to the organizers for giving me an opportunity to speak here. I'm going to be talking about some joint work with Veronique, Bazier-Matte, and Aaron Chan on the representation theory for non-orientable surfaces. So the plan for today is we're going to start by talking about the representation theory for orientable surfaces and kind of reviewing that story, and then talk about the nuances that appear when you relax that assumption and you look at things like a Mobius strip, for example. And then I'll go ahead and talk about our main results, which I'm labeling as the categorification of the non-orientable analog of triangulations of surfaces. So the motivation for the project is kind of connecting a lot of surface combinatorics and representation theory. So to an orientable surface and a triangulation of it, we can associate various algebras to it. For example, a cluster algebra, Jacobian algebra, etc. And there's really beautiful descriptions of module categories and cluster categories in terms of this topological setup. So for example, we have a nice correspondence between arcs on this surface and indecomposable rigid objects in the cluster category. And for example, we also have a nice correspondence between these collections of arcs, triangulations, and cluster tilting objects. So this is what I'm calling the categorification of orientable surfaces. And we wanted to figure out if there are any analogs for these results for non-orientable surfaces. So let's go ahead and review kind of the story for orientable surfaces. So if we take some surface, I have a disk with two closed disks removed, and we triangulate it, we can associate a quiver with potential. So we take this surface, we're going to fix the counterclockwise orientation, and we can obtain a quiver in the following way. So I'll put the quiver down here that I'm labeling QT. The arcs of the triangulation are going to be in bijection with the vertices of the quiver. So I have 6 arcs in the triangulation here, and we have 6 vertices of the quiver. And if we wanted to get the arrows of the quiver, what we can do is use the fixed orientation of the surface, scan at each marked point, and get paths in Q. So for example, if we look at this bottom marked point here, we can take the path that goes from 5 to 4 to 2 to 1. So this is one of the ways that you can produce the arrows of the quiver. And we can also get a potential on this quiver by looking at the internal triangles of the triangulation. And this will end up giving the relations in the Jacobian algebra I'll define on the next slide. So here is my triangulation and my quiver, and the potential that I get is just a combination of these cycles coming from internal triangles. So if you look at the kind of beak of this owl, 2, 3, 4, this ends up corresponding to the term in the potential B, C, D, and then there's one other triangle that gives this other term. So from here, we can get an algebra, namely the Jacobian algebra. So the way that we do this is we look at the path algebra of the quiver, and then we mod out by the Jacobian ideal, which is just given by the relations given by the potential. So the way I like to think about this, I think Anna already talked about this, but if you take one of these triangles, you just mod out by the angles or any of the two paths that you can get, and then we get the Jacobian algebra associated to this marked surface. So it turns out that the representation theory is very nice in this setting. The algebra that you get is a gentle algebra, it's finite dimensional, and the module and cluster categories are well understood using the topology. So the examples that I'm giving again are these correspondences we saw before, that arcs are indecomposable rigid objects and triangulations are cluster tilting objects, plus lots of other nice homological properties. So we want to try to give these analogous results for non-orientable surfaces and their associated quasi-cluster algebras. So I won't have time to define what a quasi-cluster algebra is today, but it's a cluster-like algebra that comes from non-orientable surfaces. It's very similarly defined. You take different arcs and closed curves on the surface, and those generate the algebras, and then you have like skein relation type things to generate it. But I'm going to go ahead and talk about those things now in non-orientable surfaces. So in order to represent these on a page, we're going to use these things called crosscaps. I actually never learned this in a topology class, so I wanted to review this with people. This crosscap is given by this symbol. It's kind of a circle with an X in it, and it denotes removing a closed disk from the surface and then identifying the antipodal points of that. So for this example, we have something that looks like this. We remove this closed disk, and to figure out what this actually is, I'm going to do some cutting and gluing for everyone to see that this is actually a Mobius strip. So if we go ahead and cut along these two edges, we can unwrap those two rectangles to look like this. So you can imagine this rectangle I've kind of deformed to this top one here, and the bottom one is this bottom one here. Okay, so now what I'm going to do is kind of do some manipulations and then glue it back together. So if you look at this top rectangle and you reflect it about this line, we get this picture, and then I've just glued this black edge with the right orientation. And so now hopefully you're convinced that this is actually a Mobius strip where we've identified these two vertical sides with the opposite orientation. So these are the pictures that we're going to be looking at to denote these non-orientable surfaces. The generators for our algebra consist of arcs and what we call quasi-arcs. So arcs, as usual, are just curves between marked points. So for example, we can travel along the crosscap here. So this is really living on the Mobius strip, so it'll look a little bit different when you visualize it. But we can have things going through the crosscap or around the crosscap, and I've drawn some examples here. The one additional generator that we're going to get for the Mobius strip are these things called quasi-arcs, which are one-sided closed curves that don't self-intersect. So the running example we'll have today is this arc you can imagine going through kind of the core of the Mobius strip. So it looks like this. This is going to be a generator of an our algebra. And what it looks like when we take the crosscap representation is something like this. Okay. So quasi-triangulations are just maximal collections of non-crossing arcs and quasi-arcs. So I've drawn all of the different quasi-triangulations for the Mobius strip with two marked points here. This is actually all connected by what are called quasi-mutations. These are what these kind of lines are. But these are going to be the objects that we're looking at today. So even though these look like they might cross, when you actually draw them on the Mobius strip, you'll see that they are actually non-crossing. Okay. So our problem is we want to figure out if we can define some sort of cluster category for these non-orientable surfaces. And the answer that we came up with is that, yes, we can define it, and we're going to give a categorification of these quasi-triangulations for non-orientable surfaces. And the main idea is we want to look at what's called the orientable double cover associated to a non-orientable surface. So it's a fact from topology that every non-orientable surface has an orientable double cover. So I've given an example here. So this is the Mobius strip, and its double cover is given by the annulus. So what we're looking at is, what does this quasi-triangulation lift to on the annulus? And so I've kind of tried to color code it for everyone. If we look at this arc X that traverses through the crosscap, this is going to lift to these two purple arcs that I've labeled 2 and 4. And if we look at the orange arc Y, this is going to lift to these two things. So what we want to do is try to study the existing machinery on the orientable double cover and make sure that when we project back down, everything still works out. The kind of hard thing about this project that I won't have time to talk too much about is this quasi-arc that goes through the crosscap like this, the core of the Mobius strip, only lifts to one thing. It lifts to this like closed loop here. So this was where we had to kind of be careful about, do we actually have a 2-to-1 map for all of the different arcs? But most of the time we do. And the idea is that we want to employ symmetric representation theory to reflect this double cover structure. So what we ended up doing was defining lots of involutions. So we have this topological involution that comes from the double cover, and we can look at what that induces on the quiver with potential. So we can define this function that I call sigma that just kind of reflects the topological structure. So we have that it fixes the potential. It's flipping these two arcs and flipping these two arrows in this case. And this is going to induce a categorical involution that we call nabla, which is essentially just looking at how this function sigma is behaving on the quiver with potential, and then kind of keeping track of a sign that we introduce here. So I'm running out of time, but I just want to get to the main results. So these involutions give us kind of the proper language to talk about indecomposability and cluster tilting in terms of these nabla orbits. So our main theorem is that we have a nice bijection between arcs and quasi-arcs on our surface and indecomposable symmetric rigid nabla orbits of objects in the cluster category associated to the double cover. And similarly, if we look at quasi-triangulations of our non-orientable surface, these are in correspondence with symmetric cluster tilting nabla orbits of the cluster category for the double cover. Thank you all for listening, and let me know if there are any questions.